Alright guys, yesterday we really focused on independent probability, so today we're going to focus on the other three types of compound probability. So dependent events, mutually exclusive events, and overlapping events. We already know what dependent events are, and dependent events are very similar to solving the probability for dependent events is very similar to how we solve for independent events. Mutually exclusive events and overlapping events are different. So if you notice, right, yesterday we looked at that word and. That means both of them are happening. Okay, I have to have both. Mutually exclusive events are events that cannot happen at the same time. And those use the word or. Okay? So and means to multiply, or, which is like what we're looking at today, means to add. Okay? So mutually exclusive events cannot happen at the same time. For example, if I'm rolling a die, I can get roll a 2 or a 4. Rolling a 2 or a 4. I can't have a die show a 2 and a 4 at the same time. Just can't happen. Okay. So overlapping events that can, are events that can happen at the same time, right? So those are just kind of like opposites, like independent and dependent events are opposites. And for overlapping events, for example, I can roll an even or a number greater than, let's say, 3. Okay. So if I look at all my different outcomes for rolling a die, 1, 2, 3, 4, 5, 6. So if I look at where I am rolling an even, right, that'd be 2, 4, or 6. And then I have a number greater than 3, right? Well, that would be 4, 5, and 6. So you can see where they overlap, right? Where both of those things could possibly happen is at 4 and 6, but I could take all of those, right? I don't really care which one it is. So when I have overlapping events, right, we add together those two probabilities, but then we have to subtract the probability of both of those happening, right? So there's 3 places that, right, 1, 2, 3 places that A works. There's 1, 2, 3 places where B works, but then there's 2 places both of them do, so I have to subtract 2. So 3 plus 3 minus 2, and that equals 4. And that makes sense with what we have here, right? 1, 2, 3, and 4. So that's kind of why that formula works, but it's also kind of how overlapping events work. Okay? So we're going to look at lots of examples with these. So go ahead and turn to the next page. Okay. So the first one is, example 5 and example 6 are very similar. If you notice, they're almost exactly the same wording. So you have to be very careful about when you have dependent and when you have independent. Independent comes when you put stuff back, right? It doesn't change those outcomes. Dependent is when you take it and you don't put it back, right? Now my outcomes have changed. So there's keywords, right? So if I look at example 5, there are 5 blue marbles, 6 green marbles, and 4 red marbles in a bag. Right? So I'm actually going to draw those. Here are my 5 blue marbles. Here are my 6 green marbles. And here are my 4 red marbles. So what is the probability of pulling a blue marble? I'm going to pull a blue marble, replacing it, and pulling a red marble? Automatically means I have independent. If I put it back, I've reset my options, right? My options have not changed. Okay, so when I put it back, replace it, Don't keep it. All different sorts of words it can use, right? It's independent. So I'm just doing what we did yesterday. I'm finding the probability of a blue marble. Right, and I have 1, 2, 3, 4, 5 blue marbles out of 15 out of 15 marbles, which is 1 out of 3. Then the probability of a red marble, and I have 4 red marbles out of 15. The problem of both of those things happening, that's not right. The problem of both of those things happening, right, is 1/3 times 4/15, right, which is, I believe, 4/45. Right, so that's just basic independent probability. Looking at example 6, there are 5 blue marbles, 6 green marbles, and 4 red marbles in a bag. As you notice, this is the same amount of marbles. 5 red marbles. 1, 2, 3, 4, 5, 6 blue marbles. What did I do? That was supposed to be green. We'll erase all those red marbles. 6 green marbles. Yeah. And then 4 red marbles. So, now this problem says, what is the probability of pulling a blue marble, not replacing it, and then pulling a red marble? So, this is dependent probability now. I'm not putting that marble back, right? I'm keeping it. So, we still kind of start the same way. The probability of blue is 5 out of 15, which is 1 out of 3. Now, I've picked one of those blue marbles, and I've kept it. So that marble no longer is in the bag. So now, when I find the probability of of pulling a red marble, right, well, I still have 4 red marbles, but how many total marbles do I have? I only have 14, so I've taken out that blue marble. Again, I can reduce it. This is 2 out of 7. Now I'm still finding the probability of both of these things happening. It's still and means multiplication. So I'm still going to multiply these two things together. The probability of C and R equals 1/3 times 2/7, which is 2/21. Okay? So be very careful on whether it says replacing or not replacing, because we know that's the only thing that changed about these two problems, and you come up with two very different answers. Okay? So make sure you're reading those carefully. Right? So that's kind of dependent events is really just an extension of independent events. All right. Looking at example 7. A bag contains 3 blue chips, 6 black chips, 2 green chips, and 4 red chips. What is the probability of selecting a black, blue, or red chip? Okay. So now this, right, with that word or, right, or is either going to tell you, okay, it's overlapping or it's mutually exclusive. So I'm going to say, okay, can I pull a blue and a black at the same time, or can that not happen at the same time? All right, I'm only pulling one chip out of the bag, so it's either going to be blue, black, or red. It can't be a mixture of them. So this is mutually exclusive. So I'm simply just adding there. I'm adding all those together. So the probability of a blue chip the probability of a blue chip, right? Well, there are 3 blue chips. I have 3, 9, 11, 15 chips. 3/5. The probability of a black chip, hey, after that one, so black. Right, well there is 6 black chips out of 15 chips. Right, this one with or, I actually haven't done anything yet. So I'm not taking that blue chip out. I can get a blue, I can get a black, or I can get a red. Okay. And the probability of the red chip, there are 4 red chips. Actually, these two can reduce, right? 3 out of 15 is 1/5. And 6 out of 15 is 2/5. So, now, the probability of blue, black, or red is simply adding these together. 1/5 plus 2/5 plus 4/5. Sometimes with mutually exclusive and overlapping events, it's sometimes easier to add without reducing. So if you'd like to do that, that's fine. Because then you see we get 13/50. Okay. The other way you can look at it, which for problems like this, when you know all your outcomes, which we've already started doing with like complementary probability, right? The probability of the complement is I have 3 blue chips, or 6 black chips, or 4 red chips. 3 plus 6 plus 4 is 13 out of 15 chips. Okay. So that works as well. So that works when you know all of your outcomes. But if we look at example 8, we don't know all of our outcomes, right? We're just given probabilities. So that's why you have to know to add them together as well. So if we look at example 8, it says a student athlete may participate in only one sport per season. In the spring season, 15% of the athletes play baseball and 23% are on the track team. What is the probability of randomly selecting a student that is on the baseball or the track team? Again, this is or, so I have to decide, okay, is this overlapping or mutually exclusive? Well, mutually exclusive because a student athlete may only participate in one sport per season. Okay, and this is the spring season. So they can't be on both of those teams, they have to pick one. So this is mutually exclusive. So, the probability of baseball is 15%. And again, I'm going to change this into decimal form by moving my decimal place back 2. So it's 0.15. And the probability of track is 23%. Which is 0.23. What's the probability of one or the other, right? The probability of baseball or track is simply 0.15 plus 0.23, which is 0.38 or 38%. Right? 0.38 or 38%. Okay? So really, if it's or and they're mutually exclusive, you're just adding them. All right, let's look at 9 and 10 quickly. Right? What is the probability of rolling an odd number or a number less than 4 on a standard die? For mutually exclusive events, I think it's so much easier just to draw the situation. So I'm rolling just like we did. All right, so I'm rolling a standard die. So my options are 1, 2, 3, 4, 5, 6. Fine. The probability of rolling an odd number, right? Well, I have a 1, a 3, and a 5. Right? So we can do the actual math, right? Remember the probability of A or B for overlapping events is the probability of A plus the probability. Ooh, that's wrong. Ooh, wrong. A plus the probability of B minus the probability of A. So I'm going to show it both ways. Okay? So the probability of an odd number is 3 out of 6, or 1 out of 2. So we can learn about that later. The probability of an even number, or not even, a number less than 4. All my numbers less than 4 are 1, 2, and 3. Right. So that's 3 out of 6. Right. The numbers where they are the same, now 1 and 3 makes the 2 out of 6. If I add all these up, right, 3 out of 6 plus 3 out of 6 is 6 out of 6, minus 2 out of 6 is 4 out of 6. This is really awesome here, guys. I'm gonna move this up a little bit. Is 4 out of 6, which is 2 out of 3. Right, and it makes sense here, right? I have 1, 2, 3, 4 out of 6 options that I found. So again, you can do it with just by drawing out all your outcomes or setting up the formula. Okay. All right, last one we're looking at is example 10. A deck of cards contains 4 suits, with each suit having 13 cards. What is the probability of randomly choosing a heart or a face card? Okay. So for this one, same type of thing. So we'll start with the probability of choosing. For this one, again, too many things to try and draw all our outcomes. This one's not as easy as, say, this one to draw all our outcomes. So the probability of a heart, right? Well, there's 4 suits. One of them is heart, so 1 out of 4. And then the probability of a face card, your face cards are jacks, queens, and kings. Okay? So that's 1 out of 13. The probability of doing both, the probability of a heart and a face card, well, out of the entire deck, which if it's 4 suits of 13 each, that's 4 out of 13, there's 52 total cards in a deck, right? There's only going to be 3 face cards that are hearts. So 3 out of 52, and that doesn't reduce, just letting you guys know. Okay? Right, so 3 out of 52. So then I'm applying this formula. The probability of A or B equals 1/4 plus 1/13 minus 3 over 52. Okay. Which is 7 out of 26. Okay, so you do sometimes, again, this one you could write out every card, but that would get tedious. So that's when that formula really comes in handy. So with these die ones, those are easy just to draw them out. But again, once you have more than 6 outcomes, it gets tedious to do that. So that's when the formula comes in handy. All right, that's it for tonight. I know it went a little long. I apologize. I will see you guys tomorrow.